In section 2.3, we will be talking about the limit laws. So I will let you guys take a look at all these limit laws here. I'm not going to go through every single one of them, but please do take a look and we'll be applying them. The one we're going to be using a lot is this one, the direct substitution law, which says that the limit of a function f of x as x approaches a equals to f of a. Now that doesn't always work. Sometimes we get um, answers that are undefined, or we get answers um, that are like 0 over 0 or infinity over infinity, which we'll talk about later on. But we can we can first try it out. That should always be our first step. Okay, so let's get to some examples. Let's say we want to find the limit of 5x squared minus 7x as x approaches -1. First thing we should always try is we should always try direct substitution. So if I plug that in, I'm going to get 5 times -1 squared minus 7 times -1, and that's going to simplify to be positive 12. So because we do get an answer, that's going to be our limit. Now graphically, if you were to graph this this function, then what's going to happen is that as we get to, so this is 0, as we get to x equal to -1, our function is going to have a limit of 12. And I drew that incorrectly. Let me draw it again. I'm sorry. It was very bad drawing. So let's say we have a function that looks like this. So this is 0. So at x equals to -1, our limit is going to be 12, which means from both directions. Remember from last section, we learned that for a limit to exist, then as a function approaches that value from both the right side and from the left side, it's going to approach the same value. That value is going to be 12. Now, when direct substitution leads to an indeterminate form, which is equal to 0 over 0, we attempt to find the limit by factoring and simplifying, or by rationalizing the function. So I'm going to talk about some like tricks you can use. Let's take a look at the limit of b cubed minus 8 over b minus 2 as x approaches 2. First, let's try direct substitution. That's always going to be our first step. So for direct substitution, we're going to get the indeterminate form, which is 0 over 0. So when that doesn't work, we have to do something to this rational function. Now, first, let's try factoring. If you recall, if you have b cubed minus 8, these are both perfect cubes because b to the third power is equal to b cubed, and 2 to the third power is equal to 8. So what we have, and you guys know what I look like, so I'm going to turn the camera off. So what we have here is, you know what, I can't right now. Take it back. I'm going to leave it on for now. So what we have here is a difference of cubes, a cubed minus b cubed. Now, when we have a cubed minus b cubed, in this case, a is the base, which is b, and b is the other base, which is 2. We're going to have the formula a minus b, which is going to be, remember our a value is b, and our b value is 2. So we're going to have b minus 2 times a squared plus ab plus b squared. So if I plug this into our formula, b cubed minus 8, that's b to the third power, minus 2 to the third power, these are our two bases. So we're going to have a minus b, which is b minus 2, times b squared plus 2b plus 4, according to this. So we have a squared, in this case a is actually b, that's b squared, plus a times b. Your a is b, your b is 2, so it's going to be 2b plus b squared, which is 4. So we're going to factor out the numerator, b cubed minus 8, as b minus 2 times b squared plus 2b plus 4. Now what's going to happen is the b minus 2's are going to divide to be 1, so we can cancel those out. And we have b squared plus 2b plus 4. So if you look at now, if you do direct substitution, we have 2 squared plus 2 times 2 plus 4, which is going to be 12. Okay. In class, I'll show you guys what this looks like graphically so we can have a deeper understanding. So here's the graph for that. And notice that we're looking at the limit as x approaches 2. So as x approaches 2, the function is undefined. But if you look at it both from the left and right side, so from negative and positive infinity, it is going to approach 12, so the limit does exist. Okay, let's take a look at another example. First, always try direct substitution. So if I plug this in, I get the indeterminate form, which is 0 over 0. And of course, feel free to pause this video at any time to copy down the information. Now, since we get the indeterminate form, we have to now factor the numerator. So a quick refresher on factoring. There are many different ways to factor. It doesn't matter which method you use whatever method you'd like. But a quick refresher is one method of factoring it's called the AC method, where we take the first term, which is x squared, which is 1, and then the last term, which is 27, it's negative. So we multiply 1 and negative 27, that gives you a negative 27. Then we find two numbers which multiply to be negative 27, and they have to add up to be the middle term, so they have to add up to be 6, which are 9 and negative 3. So they multiply to be negative 27, and they add to be 6. Then we ignore the square, and we put x on top of each. So that's going to give you x plus 9 and x minus 3. And that's going to equal to x squared plus 6x minus 27. Once again, if you need a refresher on factoring, you can email me and I can send you a factoring video, or you can Google factoring video online. But if you do need help, let me know. So once the x plus 9s cancel out, we're left with x minus 3. We do direct substitution, and we have negative 12. Once again, if you graph this, you will see a hole at x equal to negative 9. However, the limit would approach negative 12 from both sides. Okay, so these are examples of factoring, whether you have either a difference of cubes, or in this case, a quadratic that we're going to factor. These are things we can factor. Now, what happens if you have a square root? So if you have a square root, either on the numerator or denominator, we're going to use a little trick called rationalizing. So the way we rationalize is wherever the square root exists, we're going to multiply both the numerator and denominator by the conjugate of that square, of that term. So conjugate, let's say we have a plus b, then its conjugate is going to be a minus b. So it's basically the same two terms, but the sign changes, and it goes vice versa. So if we have a radical x minus 2, then its conjugate will be the same two terms, but the sign from a negative to a positive. So the conjugate would be a radical x plus 2. But before that, we should do direct substitution to plug it in, and we do get the indeterminate form. So often when a radical is involved, we can multiply both the numerator and denominator by the conjugate. So once again, the conjugate of radical x minus 2 is going to be radical x plus 2. Okay, so here's a little trick. On the denominator, we're going to leave this the way it is. The numerator we FOIL, the denominator we leave it alone. So if we FOIL the numerator, we're going to get the following. We're going to get x times x, or radical x times radical x, which is just x. Quick refresher, if you have something like this, if you have like radical x times radical x, that gives you a radical x squared, and a radical x squared is just equal to x. So when you multiply the same radical by itself, we get that term without the radical. So radical x times radical x is x. Then we have a 2 radical x and a negative 2 radical x. So those are going to add to be 0, and negative 2 times 2 is negative 4. So the numerator you FOIL, the denominator do not FOIL. Okay, do not FOIL the denominator. So if I simplify this, the middle two terms are going to add up to be 0. And we're going to get the limit of x minus 4 over x minus 4 times radical x plus 2. Now, once again, the x minus 4 will cancel out, and you're left with limit as x approaches 4 of 1 over radical x plus 2. At this point, we can do direct substitution. So if we do direct substitution, notice that we have 1 over radical 4 plus 2. Radical 4 is 2, so if I have 1 over 2 plus 2, that gives you a 1/4. And you can verify this graphically. So graph this rational function and take a look at what happens as x approaches 4. You can see that the function is going to approach 1/4. Please remember to think of any questions you guys may have, and I'll be happy to answer those during class. Okay, now let's do another one that's a little more complicated. So this is we have a rational function divided by another term. So we have 1 over s plus 4 minus 1 over 7 over s minus 3. These are called complex fractions. When you have a fraction over a fraction, these are called complex fractions. And we want to know what happens as s approaches 3. So first step is always going to be direct substitution. And if you do direct substitution, on the numerator, we get 3 plus 4 is 7. So we get 1 over 7 minus 1 over 7 on the numerator. Denominator, we get 3 minus 3. So I get the 7 by doing 3 plus 4. So this gives you 0 over 0. That's indeterminate. So when it's indeterminate, we are going to have a special method where we get rid of the denominator. So how do we do that? Step one is to find the LCD, or the least common denominator. So the s minus 3, I'm going to write that over 1 just to show you guys that there is a denominator there. And between the 7 and the s plus 4 and the 1, our least common denominator has to include all the terms. So if you multiply 7 times 1, that's 7. And then we have an s plus 4, which is our LCD. Once we find the LCD, we're going to multiply all the numerators by the LCD. So I'm going to multiply the 1 by 7 times s plus 4, the second one by 7 times s plus 4, and then the s minus 3 by 7 times s plus 4. So once again, we're going to multiply all the numerators by the LCD. And the reason we can do this is if you multiply all the terms of a rational function by the same thing, then it's like multiplying the whole thing by 1. Okay, so the LCD is 7 times 1 times s plus 4, and you multiply all the numerators, so this thing, and this thing, and this thing, by the LCD. So let's simplify this a little bit. In the first fraction, the s plus 4's cancel out, we're left with a 7. In the second fraction, the 7's cancel out, so we're left with negative 1. I'll just put a negative s plus 4, and then over s minus 3. Now don't forget to distribute that negative. So once we distribute the negative, then that's going to give us a negative s and a negative 4. If I combine my like terms, 7 minus 4, that'll be 3. So I get a limit of negative s plus 3 over s minus 3 times 7 times s plus 4. Now at this point, we're going to be using a little trick. So notice that we have the same two terms, s and 3, but the signs changed. Here, it's positive. On the numerator, it's negative. Here, it's negative. On the numerator, it's positive. So when that happens, what we can do is we can factor out our negative 1 from the numerator. And when you factor something out, if I factor out a negative 1, what I'm doing is I'm dividing the negative s by negative 1, which gives me a positive s, and 3 by negative 1, which gives me a negative 3. Because if I multiply it back, it gives me a negative s and a positive 3. So we can factor out that negative 1, which is so when you distribute, you multiply, factoring is dividing. So you're dividing these each by negative 1. S divided by negative 1 is negative s. Negative s divided by negative 1 is s. 3 divided by negative 1 is negative 3. So now we can cross out the s minus 3's. And we're left with negative 1 over 7 times s plus 4. At this point, we can use direct substitution. And if you replace the 3 with s with a 3, we're going to get negative 1 over 7 times 7, basically, which is negative 1 over 49. Okay, and I'm going to show you guys that factoring step one more time. So if I have a negative s plus 3, what I'm doing is I factor out a negative 1. Factor means to divide. So a negative s divided by negative 1 is s. 3 divided by negative 1 is negative 3. And that's how I get that negative 1 times s minus 3 from. Okay, this next one I'll do in the next video.